Okay, so yesterday we had this class exercise, and together we came up with a different solution to this one shown. This is just the one possible solution that the textbook itself suggests. And there you can see it is just a possible solution. We don't know if it's the best solution. And how would we know if it is the best solution? What we'd have to do is to work out how much is the cost of each of these distillation columns. But it's not just the capital cost. We have to work out how much it costs to run, because you can always make a distillation column bigger, many more trays, and then you would use less reboiling, less energy essentially to run that to get the same amount of separation. So there's always going to be, in the design of a distillation column, there's always going to be a trade-off between capital cost and run cost. And it in almost all cases works out that the more you spend on the equipment, the more efficient you can make it, and therefore the less it costs to run. So if you were to look at this separation solution, the sequence of separations that are shown here, you would have to work out the capital cost and the running cost of this column shown, plus the capital cost of that column, capital cost and running cost of all of the columns that are shown over here. And you can't directly compare capital cost and running cost. So essentially, we've got to take capital cost and annualize it in some way. And that is something that we'll be getting to later in the lecture. And today's lecture will be a little bit shorter than usual because we should be finishing this section of the work probably in 20 minutes or so. All right, let's move on to the next slide. When you've got a ternary mixture, it may be that you should rather use a complex set of distillation columns rather than the simple distillation column. So simple distillation columns, an example here, ternary mixture, you do the direct sequence, take off A and then B, and of course in that last one it's a binary separation, B and C. And the alternative, indirect sequence, where you take off the heaviest component first, and then you've got your binary distillation after that. So these authors from 1978 took ternary mixtures with various relative volatilities and various flow rates, and did this calculation of capital cost, running cost, and found out which of these 7 types of distillation column. Here is a pre-fractionator with distillation, distillation with a side stream rectifier, and for each of many combinations of relative volatility of A versus B compared to B versus C, they would do the full economic analysis of how much it would cost to make such a column. And so remember, there are 7 of these things. On the next slide, we'll see what their results were. It said that if you've got something that contains mainly A, here is a ternary mixture. If you've got something that contains mainly A, it would be close to this apex of the ternary mixture. And then it would make sense to use type 1. And type 1 was the direct sequence. So it would make sense then to take off A first, and then you can separate B and C next. And so any mixture that you're starting with that lies within this boundary, you would you would have the most economical solution by using direct sequence. Yes, Jacob.
So are these components A, B, and C once again ordered in order of decreasing volatility, or is there another type of ordering going on?
Yes, no, you're absolutely correct. It's always going to be A, B, C is in order of relativity. So A is the most volatile.
Yeah.
And you take
Then
it off.
B and then C.
You would be taking it off first, and that would be direct sequence. And C is always going to be the least volatile.
Okay, cool.
So
Thanks.
in a similar way, yeah, sure. So in a similar way, if you've got mostly C, then that heuristic that says take off those with the highest molar percentage, the molar flow rate first, would come into effect. And therefore you would use number 2, which is the indirect sequence. You would take off C first everywhere in this part. Okay, so that's more or less what Tedder and Rudd have done. I just want to go into more detail because they found that this applied when you have an ease of separation index less than 1.6. And the ease of separation index is looking at the relative volatility of separating A from B versus the relative volatility of separating B from C. So in other words, this ESI, you would typically have an ESI that is ease of separation index that is around 1 in most cases, I suppose. And that means that you would be using this diagram. So you see in this diagram, we've got 1, we've got 2, 3, and there's no 4. 5, 6, 7. So there's always a place for any one of those things except number 4, and we'll just go back to remind you number 4. This is number 4, distillation with side stream stripper. In other words, you take off liquid from above the feed, and then you'll have another reboiler at the bottom and put back the vapor just above that same plate. But if you have a distillation column with a side stream rectifier, that is something that does occur, and it occurs quite regularly. And perhaps the reason that this is economically viable compared to this one is because a concept doesn't require energy. It doesn't require the extra energy to run this system. Whereas this one, you would have 2 reboilers. So perhaps that influences the economics somewhat. But anyway, in none of the solutions did they find that this solution number 4 was the most optimal. Okay, so let's have a look back at this thing. Solution number 5 occupied a fairly big space when we had mostly B in the feed. We'll go back to number 5. Number 5 is a pre-fractionator with distillation. And this is something that you can apply by putting in a septum or a divider that runs downwards through the column in this way, so that you've got trays on both sides of that separator. And that way you can put in these 2 feeds and get separation. In other words, you put in the feed, this part of the column is the left-hand side of the separator. And then these 2 things come out at the top of the separator, and then you can get B being separated from A on this side of the septum, and C will be separated from B on that side of the septum. That makes it quite a economically viable distillation column. And in fact, Sassel put up one for separating octene, I think, and they received the Institution of Chemical Engineers Gold Medal Award for that design. Right, so let's go back to that one. That was type 5, and you can see the type 5 is quite a big area, and it also occurs on this side. Yes, Wilco.
Hello, Prof.
Hi.
Sorry to bother. Just a quick question. The setup for 5 with the pre-fractionator with distillation. When purifying, in that instance, I think, when you're purifying the A and B for the feed above and the B and C for the feed below, does this configuration minimize the energy cost to operate that setup with comparison to number 1 and 2?
I think it does, simply because this part doesn't require a reboiler. So the only reboiler you've got is C.
Okay,
so,
thank you.
So C alone would obviously have a larger, would need a smaller reboiler than the reboiler here in the direct sequence, because that would consist of B and C. It's a bigger flow rate, and you probably need a little bit more. You need a little bit more reboiler energy there. Yep. So it's a really beautiful design.
Thank you very much, sir.
Okay. Talking of this, in Aspen, I don't. Can't remember. Maybe somebody can remind me. Did we do? There's a normal DISTL and there's a RadFrac. I think we have done a RadFrac unit in Aspen, in our Aspen tuts, haven't we? Oh, we have done a RadFrac. Okay, good. Now with a RadFrac, you can actually do this thing of taking off a side stream from whichever tray that you like, and you can attach the liquid that's coming back. You can replace on top of any tray that you. So RadFrac is an extremely powerful Aspen tool. We just haven't done that particular one. In fact, that example that we did with cumene example, we had the CHC, hydrochlor. We had cumene and we had 3 things that we had to separate, and this turned out to be quite a useful way of separating those 3 in that particular cumene example. So you can go and look at the TUT, which is still on TickUp, the next TUT I think that we haven't done in Aspen yet, and have a look at that. RadFrac is powerful and makes it possible to do that sort of thing. Right. So now, if we look at an ESI of greater than 1.6, you'll see that we don't even have the possibility of using the direct sequence. So the type 1 has disappeared totally from this map. And this one, type 3, has increased. So boundary here has started to move over as you go from, let's say, ESI 1.5 up to ESI 1.7. This boundary has started moving across, and now that boundary lies this way, and it's taken over all of that area that 1 used to occupy. and now it's occupied by number 3, which is the prefractionator with distillation. No. 3 is not that. Sorry. Let's go back to 3. 3 is there. Side stream rectifier, the same thing that would be useful in the Q-mean example. Okay, so when it means that when A is easy to remove, because the ease of separation index is greater than 1.6, it means that it is by far easier to separate A from B than it is to separate B from C. Then there's no sense in using the direct sequence, because that will involve more reboiler energy. Of course, this number 3, if we go back again, number 3 doesn't have a reboiler here. You've just got the 2 condensers, and you've only got the single reboiler with a single component coming out, so therefore you tend to use less energy there. Right. Okay, so this is a really easy thing to apply. And what it also means is that I'm going to go back to that example that we had. In this example, here is a set of 5 components. Here is a set of 4 components. And then immediately we go to two binary distillation columns. So there's no place in this sequence where we actually have three components. But when we as a class looked at what would be a good sequence to use, we thought that the first separation would be here between N4 and C5. And if we did that, then we would have a 3-component system at the distillate of that column, and a 2-component system, stream at the bottoms of that column. Now, once we've got this 3-component system, we can go and apply Tedder and Rudd and have a look at what would be, depending on the molar flow rates, we would be able to choose a suitable distillation for that 3-component system. So essentially, this is what I would expect you to do in the exams and tests, is you can choose using heuristics. Let's say I do a 6-component system. You could use heuristics to choose the separations until eventually you land up with a 3-component system. And as soon as you have a 3-component system, the Tedder and Rudd method is going to give you a much better answer, because this Tedder and Rudd method chooses the distillation column system that based on economics. And that's essentially what you're supposed to be doing when you're choosing a separation sequence. Always choose a separation sequence that has the lowest capital cost, not capital cost, lowest annualized running cost. Right. Now we can move on. So this is really straightforward. This is an algorithmic method. You can go and plug in the numbers, read it off the graph. One of the things you must just get used to doing is reading ternary graphs, and we'll be doing a lot more of that. But essentially, if you want to look at a line that contains equal amount of A, it is a line that runs from where the pointer is now across that way, equidistant from A. So this would be perhaps 75% A, and it runs there. That's all 75% A. This is 75% A with 25% B, and this is 75% A with 25% C. Okay, so you must just get it clear in your minds how to read these ternary diagrams, and then apply Tedder and Rudd's method is really straightforward. Right. when simple distillation is not practical for all separators. Other types of separators must be employed, and the order of volatility may be different for each type. So think back to that example we had when we had propane, butane, butene, pentane, and then we had to use a mass separating agent to do extractive distillation of the butenes. The furfural would help to extract the butenes from the butanes. This is the type of thing that we're talking about. So when simple distillation is not practical, we've got the option of using extractive furfural, or we've got the liquid extraction option, such as adding water to an organic mixture. Now, if they are all two product separators, in other words, let's talk about a liquid. You've got two liquids and you separate the two liquids from each other. That means you've got two product separators. And if T equals the number of different types, the number of possible sequences is now given by T to the power, the number of products minus 1, times the number of separations, NS. And that gives a much greater number of total possibilities if you can do extractive or liquid extraction on any one of those columns. So it's not something that is very important. What we're doing here, this number, this little formula, it's not particularly important. It's just to illustrate that the number of possibilities gets very big as soon as you can have ordinary distillation, extractive distillation, and liquid extraction. But when you think about it, there's a very specific time when you want to add, a very specific reason that you want to add furfural into that butene mixture. And so therefore you know where you're going to be adding the furfural and where you're going to be doing the furfural extraction. In other words, extractive distillation. And so it is not as serious as this, how quickly the number of possibilities increases. So I'm going to go over it fairly quickly. This is the example that we were talking about, propane. Then we've got 1-butene, which is the next most volatile component, then N-butane, then cis and trans butenes, and then pentane. Now, a thing I wanted to point out, previously we had that little logic diagram that said how you can design the pressure and the temperature of distillation columns when you're doing ordinary distillation. Have a look at these critical pressures. And I was talking about how organic molecules tend to be in the same range of critical pressure, which is above 30 bar and below 50 bar, essentially. If you have a look, this is the highest one, 4.17 or 41.7 bar, and the lowest one is 33 bar. So this is the reason that you don't go more than about 29 bar pressure if you want to design a distillation column, because you know that you want to keep well away from the critical temperature and pressure of the system. Okay, that's just an aside. So if you've got ordinary distillation and extractive distillation, as we have with this system, remember we wanted to add the furfural, and therefore P equals 4, then the number of separators equals 40. But since 1-butene must also be separated, P equals 5, and that increases the number of separations to 224. So essentially you want to reduce the number of sequences, and you need to eliminate unfeasible separations and enforce ordinary distillations with separations with acceptable volatility. So let's see what we can enforce as ordinary distillation in this system. There we go. Here are the adjacent binary pairs, the alphas, and that one you would obviously want to do ordinary distillation. And certainly this one is very easy to do ordinary distillation. So you'll say that for those two separations, you'll always want to do ordinary distillation. This one, it's infeasible to do ordinary distillation because we've already said you can't do ordinary distillation if your alpha is less than 1.05. So we have to do something to separate butane from trans 2-butene. And that's where we added the furfural. Use of 96% furfural increases the volatilities of paraffins. So it will increase the volatility of butane, and the trans 2, the butenes, will tend to go with the furfural, including this butene, which is even more volatile than the N-butane. And ultimately what it means is, if you look at all of the possible splits, now we know that we're going to be taking out all of the butenes together with the furfural, and then we'll separate the furfural. And therefore the splits to be considered, with all others forbidden, are A from B, E from F, B from C, A from C, and then this is C from B using furfural, and C from D using furfural. So I'm going over this fairly quickly because it's not particularly important. It's really common sense. If you're using the furfural to do a certain specific job, like removing the olefins from the plain, what are they called? The olefins from the normal hydrocarbons. You know you're going to use furfural for that, and you know what the volatilities are. So you know exactly what distillation columns you're going to be using. And that's essentially what the conclusion of this section is. Right. This is a very important slide. So I was talking about this balance between how much you spend on capital versus how much it'll cost to run your distillation column. And what we're saying is that we're going to work out the capital cost, and then we're going to annualize the capital cost. So if we annualize the capital cost, we can add that annualized capital cost to the running cost, and we will have a single cost that we can compare one distillation column with another. Okay, so if you've got a separation sequence that you want to put economic values on. In that class example, we had 4 distillation columns. For each separation, for each of those distillation columns, you can assume 99% recovery light key in the for the heavy key, and then set the distillate and bottom column pressures using that logic diagram that we did yesterday. Estimate the number of stages and reflux ratio by the Fensker Underwood Gilliland method, and that is DSTWU in Aspen Plus. Select the tray spacing, 2 foot or 60 centimeters, and calculate the column height H. If you've got the column height, then you can calculate the tower diameter using the fair correlation for flooding. So if you've got too much gas, then you can too much vapor for a certain diameter, then you will get entrainment of the liquid into the tray above it, And so the fair correlation will say how big must the diameter be so that you don't get that entrainment of the liquid into the column above it. So then you will have the column, the tower diameter D and the tray spacing H, the height of the full column, and now you can find out the capital cost of the tower. And that's a whole new thing, and you'll be doing that in CPS next semester, CPS 421. Right, then you size and cost the ancillary equipment, and then you can get capital costs for the condenser. You know what its duty is in kilowatts. It's the reboiler and the reflux drum, and you sum those to get the total capital investment for the distillation column. So for each of those four things, you'll be able to get the total capital investment for each of those four columns. And then you can add the cost of the heating and utility, heating and cooling utilities. And that is, that COS stands for cost of sales. Cost of sales is a running cost, essentially. Then you can compute the annualized running cost, this CA that we're talking about up here, computed by assuming a return on investment, typically R equals 0.2, annualized capital cost is cost of sales, plus R times the total capital investment. So if you say 0.2, if you say R equals 0.2, then we are assuming that the payback period for that capital is going to be 5 years, because we can take the total capital investment and divide it by 5 or multiply it by 0.2 to equilibrate the capital investment into a running cost. And then you can add those two running costs together, and then you have a single annualized cost, so that you can compare one distillation column with another. All right, so here's an opportunity to force people to put up their hands. Right, Jared.
If you have information with regards to the duty and stuff like that and your sort of actual cost to supply that energy, would it not be better to use that in your annual running, or in your annual costing or annualization, rather than a default of 0.2?
No, because what you're talking about is a running cost. Weren't you talking about running cost there?
Yeah, I'm probably just confusing myself, don't worry.
Yes, because that cost is the running cost. This R times the capital cost. Capital cost is different. It is important because you've got to borrow money. You guys have done a course, business management or something like that, I think last year. Am I correct? And anyway, in that course, there we got a tick at least. In that course, you learned how to do a discounted cash flow. You'll be doing that again with Barent next semester. But the discounted cash flow is the correct way of working out point one. Okay. Yeah, that's a good point. I'll get to that. Discounted cash flow is a way of working out what is the net present value of an investment that you make now. So, that would be the correct way of doing it, but this is just a shortcut way. Rather than doing a discounted cash flow over 10 years, and you've got to know when investing this capital, are you investing it over 2 years or 3 years, and how quickly do you come up to production rate, and that would affect, all of those things would affect the discounted cash flow or the net present value of your investment. But this is just a quick way of showing some balance between the total capital investment versus running costs. Okay. Point number 1, set the distillate and bottoms columns pressure. I'm going to go back. Let me just see if I can go back over here. It'll be easier. I'm going to go back to that thing that I was talking about, this one, this slide. Oh, there we go. It's not so difficult. So this was at the last lecture. We said, how do you work out what pressure to operate your distillation column at? And depending on whether you need to use a high pressure or not, and if you have to use a pressure greater than 215 psi, or greater than 365 psi, 28 bar, 415, 28 bar, then you have to use a refrigerant for your condenser, which of course is much more expensive than just using cooling water. And ultimately you come out at the temperatures and pressures at which you're operating your distillation column. Right, so that is point 1 of that slide that we were talking about. I'm just going to go back to the slide we were at. Yes, Louis.
Just stay on the slide real quick.
Oops. Yeah, I'll go back. It's easy enough. There it is.
It says there's something about reset pressure distillate to 30 psi if it's less than 30 psi. 30 psi is like 2 atmosphere.
Yes.
Is there a specific reason for that?
Yeah, I've seen that before. Yeah, I always talk about 100 atmosphere, so that you don't use a pressure vessel. You don't want to have the possibility of air coming into your distillation column, because then you can have an explosion. So if you operate with a slight overpressure, you're fine. It just seems a little bit more. That's 2 bar pressure. Seems a little bit more than you really need. But yeah. So I just work on 100 kPa atmospheric pressure type of distillation. But when you run a distillation column at 100 kPa, you will always try and operate it under a very slight vacuum. Very slight pressure, positive gauge pressure. Okay, let's go back to the original slide. Right. That was annualizing. So that information thing is a link that goes back to the slide we were looking at. Right, next, now we're going to go and look at our system of propane, and where A is propane and B is butene, 1-butene, and C is butane, and so forth. And we're going to have a look at how we're going to do this costing and decide which is the best sequence. So these are the possible separations that we can do at the top there, and this is putting out a tree of all of those possible combinations. So if we start with an A/B separation, 2, it would be an AB/C separation, and so forth. So you can do your separation anywhere along those things there. And once you've separated A, there's A coming off. Then the next thing will be a BCDEF separation, and there would be, and you'd know what are the flow rates of B, C, D, E, and F here, and you could go and do that calculation. What's the annualized capital cost? What's the annualized cost of running that distillation column? And it is 249, let's call it $1,000. This one would have been 33, because remember, A was very, very easily separated from B. And so that one's only 33 $1,000, call it, whatever units we'll be using. This one is $249. And once we've done that separation, we've got CDEF, and CDEF we can do F first, it'll be 68, but if we do C/D, it'll be 582. Then we'll have a DEF, and we can separate that with the only possible one we could do is the EF. That's from this list up here. And finally, you can do the binary separation of DE, and that would be 35,000, and you can add them all together. So 151628, there's that distillation column. You can work out an annualized cost for 151628, and you get $900,000 per year. Similarly, we can go across on the red one, and we can add up to those things, and we get $872,000 per year. This one, we can go down, and once we go past this distillation column, immediately we've got 1,047, which surpasses the total cost on that sequence, on that separation train. So you can actually stop at that point. Here we've got 76.2, and then you can carry on and do the two different things. This one works out 985. Immediately you'll know that it's going to be more than the 872,000. And so that way you can have a look at all these possible trees and decide which one is going to be the best tree to go on. And similarly, you can do the same for all of these possibilities, 1, 2, 3, and 4. So let's carry on. Here is number 2, and we can go down that way. This one is very similar. 8, 10, 22. And this one, and eventually 10, 22, yeah. And eventually you can work out which is the optimum one, going down, starting with 2, and with 3, 867,000, and eventually you could look at all of the various branches of that tree and decide which one is the cheapest. And I think it is the 857. This is 867. There was an 860,000, so let's just go back. 860, 872. So the 860,000 would have been the cheapest way of doing that separation. And so that's the correct way of going about it, but it's a lot of work. Once again, because you're talking about a great number of costs, when you run this plant for 10 years, so you've got an annualized cost, and you multiply that by 10 years or 20 years, you are talking of a great difference between making the one design choice and the other design choice. So you should not be shying away from doing all of this engineering work of costing each one of these possible columns. So eventually you land up with the lowest cost sequence, showing where you've got propane and butene, and then you can distill butene from the propane, and then you mix with the mass separate from the two butenes that you got using the mass separating agent, the peripheral, gives you your $860,000 column. Okay, so that's a lot of engineering work in the design phase, but it's really important that you put in that work in the design phase because the cost savings from 860,000 versus 867,000 is significant when you multiply that by 10, and it could easily be more than the engineering work that's involved with that. And that is the end of the lecture. Oh, it didn't take us 20 minutes. Okay. Yes, William. We don't have, chats. We don't have a chat session, no. No, I'm not going to be using that for class or anything. Actually, there's not much more classwork left. So I'll just be doing lectures, and I'll be doing some class tests or polls or whatever during the lecture periods. Yes, Jacques Louis.
So just a bit of like forward thing here. Seeing as we don't really have the thing to look forward to using Aspen in our design project next semester, because in all likelihood we're not going back to campus this year. It would actually be quite useful to maybe start learning another open source type simulation, process simulator. Do you have any ideas on that?
Yes, yeah, DWSim, like Beatrix has just said, is what we will be using, as you say, in all likelihood. I've looked at DWSim and it looks really easy to use. When we chose to use the Aspen Plus, it was simply because when you go out and work in the industry, it is most likely that that's what they would be using, and therefore it will be good if you're already trained in Aspen Plus. But all of these process simulators are very similar. So yes, I think it would be a good idea if I showed you DWSim at some stage, and how to operate it, and you guys can all go and look it up. Go and look up the DWSim and download it on your own home computers, because it is very likely that we'll be using DWSim for the design project next year.
Okay, cool. Thanks.
For that reason, the design project, I'm probably going to choose something that's got components that are for which the properties are readily available. One of the nice things about Aspen is that it's got a very good database. Okay, Jacques Louis?
Yeah, no, cool, thanks. Would it be possible to maybe later on, we still have like 7 weeks left, to do a couple of those Friday test sessions on DWSim, like we would have done for the Aspen?
Yes, it's quite possible. I will have to see how we do it, how we get around to doing that.
No, cool.
Thank you. That sounds great.
Cool,
okay,
thanks.
Good stuff. Thanks for attending today's class, and see you on Monday next.